Allô, 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 allô. Ok, m'ajouter un adobe, prenez place s'il vous plaît. Le temps passe, il est 11h, 11h35 minutes. 11h35 minutes,
La destruction des écosystèmes menace les espèces endémiques, mais aussi la santé humaine. À Madagascar, la pollution de l'air a fait plus de 46 000 morts en une année. Nous avons réduit en cendres plus de 100 000 hectares de forêt.
Sous le haut patronage de son Excellence Monsieur Angélique Ratuel, président de la République de Madagascar, le MED, en collaboration avec le gouvernement allemand, à travers le programme Page de GIZ, avec le concours du MESUPRES et du MINSAM, organise un symposium international sur la biodiversité et la santé le 19 et 20 novembre 2021 à l'hôtel Paupap Matsang.
Agissons ensemble pour la biodiversité et notre santé.
Prenez place s'il vous plaît, parce que... Alors, mesdames et messieurs, prenez place, s'il vous plaît. Prenez place parce qu'on va commencer la cérémonie. On va commencer la cérémonie de remise de matériel du ministère de l'Environnement et du Développement durable au ministère de la Santé, mais également au ministère de l'Enseignement supérieur parce que ces matériels seront utilisés par le centre hospitalier universitaire de Mazang. Alors, mesdames et messieurs les ministres, je vous prie de vous lever pour cette... Ok, madame, vous avez la parole pour officiel. Messieurs, mesdames les journalistes, tout de suite après cette remise, il y aura donc le point de presse qui va se faire ici dans la même salle pour que nous gagnions du temps.
m'avoir donné la parole. Chers collègues ministres, aux représentants de la coopération allemande, mesdames et messieurs, chers journalistes, je suis très heureuse d'être là aux côtés de la coopération allemande, du ministère de l'Environnement et du Développement durable, pour offrir ces matériels pour accompagner donc le CHU Andrew de Majanga pour les questions de santé, notamment dans la lutte contre la pandémie du coronavirus. Dedans, il y a deux types de produits. D'abord, il y a des réactifs de détection pour le SRAS-CoV-2, donc des tests PCR de dernière génération. Il y a 30 000 tests donc, dans ces deux boîtes. Et l'autre élément, c'est un appareil pareil de dernière génération que l'on appelle Cycler PSR. Et donc, grâce à cette coopération que nous avons avec la GIZ et qui soutient très activement nos trois secteurs, la santé publique, l'environnement et la recherche scientifique. Donc, nous sommes vraiment ravis de vous octroyer ces matériels. Pour le Cycler, c'est un appareil qui fait plus de 100 kg. Donc, il est en cours d'acheminement. Ça va arriver sous peu à Mahazang. Mais on vous montre un petit peu comment c'est cette machine de dernière génération. Et donc, c'est 30 000 produits pour le test PCR. Merci beaucoup. Petite précision, puisque c'est très important, les matériels qui sont donc offerts au CHU Andrew de Majanga sont d'une valeur de 200 000 € entre l'appareil dernière génération et les tests, 30 000 tests PCR. Et nous espérons en tout cas que ça va vraiment contribuer à la lutte contre la propagation du Covid et surtout accompagner les tests pour les populations à Mahazang. Merci beaucoup.
Madame le ministre de l'Enseignement supérieur et de la Recherche scientifique, Madame le ministre de l'Environnement et du Développement durable, Mesdames et Messieurs les membres des PTF, ici près, aux responsables selon vos rangs et grades respectifs, honorables invités, Mesdames et Messieurs, mes premiers mots sont de vous adresser mes remerciements les plus sincères. Le ministère de la Santé et le ministère de l'Enseignement supérieur, vu que c'est un centre hospitalier universitaire qui est destiné à la formation des futurs médecins, qui est bénéficiaire de la donation aussi présente, les deux ministères expriment leur reconnaissance envers le peuple allemand à travers le programme page 2 de GIZ pour cette dotation matérielle du laboratoire du centre hospitalier universitaire Bzaga d'Androuva, à savoir donc ces kits de réaction et un appareil d'une valeur estimée à 200 000 € et également vont accompagner cette donation et renforcement des capacités des agents de santé par rapport à l'utilisation du matériel. La capacité du système de santé va ainsi augmenter pour répondre à de multiples défis, particulièrement pendant la pandémie de Covid-19 qui a été mise à rude épreuve, et la dotation de ces appareils, de ces réactifs, vont alléger un peu le système de santé du côté de Mahazang et aux alentours. La coopération allemande avec le programme de la GIZ a déjà soutenu le ministère de la Santé à travers la dotation de nombreux matériels et équipements de protection, d'hygiène et de prise en charge Aussi, nous exprimons, les deux ministères, nos profondes gratitudes à la coopération allemande et la GIZ pour cette dotation en matériel au laboratoire qui témoigne son soutien continu et palpable pour le secteur santé. Soyez rassurés, messieurs et mesdames, les membres de la GIZ, et à travers vous, nous remercions donc l'ambassade de l'Allemagne et à travers l'ambassade de l'Allemagne, le peuple allemand. Soyez rassurés que nous allons, à travers l'équipe d'Androuve, conduite par son directeur d'établissement, ferons bon usage de ces donations et nous veillerons à la maintenance et à l'entretien de ces précieux matériels et équipements, agissant ensemble pour la biodiversité et notre santé. Mesdames et messieurs, je vous remercie.
Donc nous remercions les membres du gouvernement pour cet échange avec les donations. Après cette cérémonie, donc tout de suite nous allons faire le point de presse juste à côté. Mesdames et messieurs les ministres, vous allez donc assister à ce point de presse. Et mes amis journalistes, parce que le temps presse, essayez de raccourcir. Azon fasalaban tupko raimeta takelo lavdaf takelo. Inartoko misaotra betsaka ny raha-panao gazety kamba dia mbola oaka mbola misy kely ministre ny fampianarana ambony tompoko sy ny fikarohana ara-tsiansa. Misaotra tompoko. Merci, mesdames et messieurs les journalistes. Donc, on va reprendre notre symposium. Alors, je prie la présidente de la séance. Zafadrina tompoko ny misolo tena ny professeur Ratsimbason Arsène zany miakatra ety ambony. Madame la Présidente, je vous donne la parole.
Merci beaucoup de m'avoir donné la parole. Mesdames et messieurs, nous allons reprendre notre journée et en souhaitant la bienvenue à celles ou ceux qui viennent de nous rejoindre pour cette seconde partie. Nous voici donc arrivés au thème numéro 6 qui s'intitule « Élimination des agents pathogènes des écosystèmes, approche temporaire et permanente ». Il sera question de l'éradication des agents pathogènes des écosystèmes en mettant en exergue l'éradication de la malaria dans l'ancienne Union soviétique et le suivi épidémiologique du paludisme à Madagascar avec l'évaluation des besoins locaux en matière de contrôle. Pour ce thème, nous avons l'honneur d'accueillir deux intervenants, à commencer par le professeur Lukachev Alexander. Il a obtenu son diplôme en 1999 et a poursuivi une carrière en virologie. Ses recherches portent principalement sur l'évaluation de la taxonomie des virus avec un accent particulier sur des infections virales émergentes. Ces études ont porté à la fois sur les infections humaines émergentes, telles que la méningite à entérovirus, la fièvre aphteuse, lymphatite transmise par le tic et les événements évolutifs anciens qui ont façonné le monde moderne des virus. Depuis 2017, il est directeur de l'Institut Martinovski de parasitologie médicale, de maladies tropicales et à la transmission vectorielle à l'université Tchernov, Moscou, Russie. L'Institut a joué un rôle clé dans l'éradication de la malaria, du paludisme et d'autres infections parasitaires en Union soviétique. Actuellement, l'Institut se concentre sur le traitement et la réduction du fardeau des quelques maladies parasitaires restants, ainsi que les questions fondamentales de l'évolution des virus. Le deuxième intervenant, c'est le professeur Ratimbassou Claude Arsène, qui est présenté ici par Dr Rakutarsoua Arinumenzanahari, CDT à l'université d'Antananarivo. Professeur Arsène Ratimbassou Arsène est titulaire du diplôme de doctorat d'État en médecine, faculté de médecine d'Antananarivo depuis 1996 et du diplôme de docteur en sciences, technologies et santé de l'université Victor Ségolène Bordeaux II et de l'université d'Antananarivo. Faculté de sciences depuis 2011, il a obtenu son diplôme habilitation à diriger des recherches en 2015 à l'université d'Antananarivo. En parallèle, il a suivi de nombreuses formations et obtenu plusieurs diplômes complémentaires. À ce jour, il est co-acteur de 60 manuscrits publiés dans des revues scientifiques internationales, à comité de lecture et de participer à de nombreuses réunions scientifiques nationales et internationales. Il est membre de plusieurs sociétés savantes, la Société Pathologie Infectieuse Académie de médecine de Madagascar. Il a été nommé comme chercheur associé à la case Western Reserve University. Depuis 1996, il a occupé de nombreuses fonctions, tout d'abord à l'Institut Pasteur de Madagascar, dans l'unité paludisme 1996 au mois de mars 2001, puis l'unité épidémiologique en 2001 et 2009, puis à la Fondation Mérieux en tant que premier responsable et concepteur du centre infectiologie Charles Mérieux 2010-2013. Donc, maintenant, nous allons donner la parole à monsieur le professeur Alexander.
Thank you very much, and thank you for the invitation. Could we start with the presentation? So my original qualification is virology, and I would like to focus on yet another dimension in virus evolution and emergence of viruses. But before I do that, I would briefly introduce the institute which I am now heading since 2017. The Marsanovsky Institute of Parasitology and Tropical Diseases was the Central Russian Institute on parasitology, founded over 100 years ago. It played a key role in eradication of many parasite diseases in Soviet Union, most importantly malaria. Since 2002, this institute is within a section of Medical University. And the main achievement was, of course, eradication of malaria in the whole Soviet Union. It was not an easy task. It took over 50 years, and it was achieved in 1953. As you can see on this graph, it didn't go smoothly. There were unpleasant setbacks in this program, and it took a lot of effort, a lot of persistence from all parts of the society. Just to remind you, in 1949, Soviet Union got its nuclear bomb, and it achieved spaceflight. So elimination of malaria was a task comparable with these two major technical achievements. It is not an easy task, and it indeed requires a lot of effort, a lot of persistence from all parts of the society. Now we have each year only about 100 cases, and all of them are imported. So we have mosquitoes, but we do not have transmission of malaria within the country. The institute was also heavily involved in cooperation with with developing countries all over the world. It hosted WHO courses on a regular basis, and it participated in elimination of parasite diseases in about 50 countries in the second half of the 20th century. Now the institute is smaller and more focused on internal issues. So now let me pass to the main topic of my presentation. This is a genome of hepatitis D virus. So here is implicitly the genetic code of this virus. Just 4 genes, just so much genetic code, and yet this virus is one of major problems of healthcare. About 100 million people are infected on Earth. So how does such a primitive organism with such a little genetic code, which is about 1 million times more primitive than our genome, how viruses are still able to compete with such complicated species as higher organisms? Indeed, if we look at viruses and compare them with the most efficient achievements of human technology, here are 2 electron microphotographs on the same scale. On the left is element of a modern microprocessor, and on the right is poliovirus. Poliovirus in the same volume and the same size can hold 15,000 times more information, plus protection of that information, penetration into the cell, hijacking the cell, and propagation. So viruses are many orders of magnitude above anything that human technology is able to create, and we still need to understand them. But another dimension of complexity and another dimension of problems for us comes from evolution of viruses. In most viruses, their replication systems that copy their genomes do not have error correction function. And as a result, RNA viruses make about one mutation per each newly made genome. Replication cycle of a virus takes just several hours, and in one cycle, one virus can produce 1,000 to 100,000 new viruses. So viruses can generate genetic diversity many orders of magnitude faster than other organisms. And in fact, even in one infected person, for example, in one population, there are no two same viruses. They all differ by one or a few mutations. In many cases, we do not even notice it when we analyze viruses. Most of these mutants are crippled. They are not competitive enough. But some of these mutants allow virus to quickly adjust to new conditions, either within an organism or when switching species. The prominent example is poliovirus, for example. If we design a poliovirus which does not make mutations, it's possible to do in the lab so that the virus will copy its genome precisely. So such precise virus is not able to cause poliomyelitis. Because to cause poliomyelitis, to infect central neural system, the virus must mutate. If it does not mutate, it just replicates in the gut. It doesn't cause poliomyelitis. So mutation is the way the virus creates a dimension within a population. And to further complicate this system, viruses also recombine. Why do I have different slides? Okay. So to further complicate the system, viruses also recombine. They exchange parts of their genome, and they can further increase complexity of their population and produce new variants. And to yet further complicate the system, different parts of viral genome can behave in different ways. So it is possible. Could we somehow achieve the same slides here and there? So to further complicate the system, different parts of viral genome can behave in different ways. It's one molecule, it's a holistic molecule, but evolutionarily one part of this molecule can evolve by one rule and the other part evolves by another rule. And unlike in other organisms, so if we look at higher organisms, the time scale of their evolution is many years or hundreds of years or thousands of years. And the population is confined to a forest, a field in most cases. For viruses, the time scale is from days to years, and the space is global. So the viruses here in Madagascar, in Germany, Russia, are affected. They commonly spread between very distant countries over just a few weeks, and it's a common epidemiological space. This complexity of populations is the mechanism that allows viruses to conquer new ecological niches, because this diversity creates a spectrum of variants which are able to invade new species efficiently if there is such possibility. It doesn't change there. And indeed, viruses do frequently change their hosts. So if we look from ecological perspective, for a virus, it's a detrimental strategy to be adapted to a single host. For example, take some prehistoric animals, take dinosaurs. They had their viruses. Probably the viruses were perfectly adapted to them, but the dinosaurs are extinct, and so are their viruses. So the main strategy of viruses is to switch species. It's the way they elaborated over millions of years to survive, fit to its host at the moment. It's more important how it is adapted to switching hosts. So viruses always switch hosts. In nature, they do it every few years, and this is what we are now exploring as virologists, because we got that understanding only in the last 20 years. It was all hidden about year 2000. Now we know that in nature viruses do switch hosts. When it happens between a bat and a lemur, we in most cases will never notice. So it all stays under the water. It's all hidden. But sometimes there are spillovers either directly into human populations or first into domestic animals and then into human populations. And these are the cases that matter for us as humans, and these are the cases that get most attention. But again, these cases are just a tip of an iceberg, because in nature this mechanism happens for millions of years on a constant basis. And just to make it clear, for a virus from evolutionary perspective, it's not beneficial to be virulent. So there is a very clear distinction between virulence, ability to cause a severe disease, and fitness, ability to survive on a long-term time scale. For example, take example of a bird flu virus, which is very virulent. It causes very severe disease, but it replicates deep in the lungs. And when people call, they do not call the virus, they do not spread the virus. And viruses that cause common cold, which is not a severe infection, spread very efficiently, so they circulate in human population, and bird flu gets extinct by itself. So for viruses, they do not want, if I can put it so, for them there is no evolutionary advantage in causing a disease, but it does happen when they are not adapted to our species and we are not adapted to them. As it has been said several times today, most of the emerging infections emerged by transfer from animals, by zoonotic transfer. And already in the 21st century, we had quite an impressive list of emerging infections. But we have to conclude that it is most likely just the tip of an iceberg, because most likely viruses tried to emerge. They attempted crossing species barrier between animals and us much more frequently. And only these few were able to establish themselves in different ecological niches. So there is always a pressure for emergence of new viruses. We do not know when will be the next virus, but this pressure is absolutely constant. It happens now in every part of the world, but mostly in tropical regions with high biodiversity. And because virus polymerases make errors, these errors accumulate at more or less constant rates in viral genomes, like rings on a tree. We can trace evolution of viruses with a pretty nice precision. So we can infer when they crossed species barriers and when they emerged in the population. These methods have their limitations, but on a time scale of a few hundred years, they are pretty precise. So again, as it was already said today, many infections that were called bibliaic, that were considered ancient in the textbook when I studied at the university, are actually emerging infections. For example, the rabies of carnivores. It was very clearly described over 3,000 years ago. But the molecular evidence suggests that all current strains of carnivore rabies on Earth have a common ancestor 700 years ago. So the virus emerged, got extinct, then emerged again, then got extinct again. Crimean Congo hemorrhagic fever, which you probably also have here in Madagascar, or at least for sure it's present in South Africa, it was described in Central Asia by doctors of that time 1,000 years ago, but in South Russia it emerged only 250 years ago. So this ancient zoonosis is actually an emerging infection. Tick-borne encephalitis. Its emergence was suggested to take place at about the end of Ice Age, 10 to 20,000 years ago. But most of its spread in Eurasia and in Europe specifically was only after year 1600 and was mostly driven by human activity. I would come back to the example of rabies because it is a disease relevant for both of our countries, for Russia and for Madagascar. In Russia, we did the research and found that the most recent common ancestor of all rabies in Russia existed only 150 years ago, which means that although it's an ancient virus, although it was with humanity for all its history, in our country it all emerged very recently. Now you will ask me, can we trust these data, how reliable they are? And we are lucky to have some field reports, some field evidence. For example, this node, emergence of rabies in foxes on vast spaces from Caspian Sea and to Mongolia. By mathematical methods, it occurred in 1948, and by field records, it was first recorded in 1946. Or, for example, spread of Russian variant of rabies virus to West Europe, we inferred it mathematically to occur in 1939, and indeed there are reports from this year that infected foxes were crossing the border with Germany. So on a short time scale, these methods are really precise and they allow to trace what have been happening with viruses decades or centuries ago. And behind this picture is really a long story which could take an hour by itself. So in different parts of the world, evolutionary profile of the same virus can be very different. In world regions with temperate climate and with a higher level of hygiene, there are waves of emergence and extinction, for example, of enteric viruses. But in tropical regions, there is very high diversity of these viruses. They persist. They often cross species barrier with primates, with synanthropic primates. And there is a reservoir in tropical regions which produces regular waves in regions with tropical climate. So it's not possible to understand the epidemiology of these viruses in one part of the world without considering other parts. And with time, the risk of emerging infections is only increasing. This is a picture from American textbook. So the number of days it takes to circumvent the globe, which is now about 1 day the population in the United States here, and the number of dams, which is a correlate of interaction of humans with nature. I'm sure this chart is the same for every country. It's about the comparable for Madagascar. We see that the conditions for emergence of viruses are only increasing. So a natural question is there a risk of a Judgment Day virus, a terrible virus that will wipe out a significant part of the population like in Hollywood movies? The viruses that are adapted to humans are generally not a serious threat. So we all have common cold. If we screen population in this room, we will find a significant number of harmless viruses. Our population manages, our immune system manages them very efficiently. Emergent zoonoses can have high lethality, indeed, and in natural conditions, they do not spread quickly beyond one village, for example, one town. But the cities we live in now, the cities which have grown tremendously over the last 100 years, are a situation that have never existed. If you take bats, they have always lived in caves. They lived in populations of thousands and hundreds of thousands of bats. Humans have never lived in such huge populations. Humans have for millions of years lived in small groups of 30 to 50 to 100 humans. So our immune system, our species is not adapted to such a high population density. And our cities are an ideal place, an ideal environment for virus spread. Now, if we look at SARS coronavirus 2, which is one of the most significant events in public health over the last 100 years, it's not a major event on evolutionary scale. Because if the virus emerged 200 years ago, nobody will notice. The fraction of population older than 60 was negligible. People died a lot of other causes. And we can feel the impact of this virus only because our health system is so good that we have a high fraction of elder population and high population the density. So can it be worse? Indeed, if we look on a rabbit Judgment Day virus. In Australia, rabbits are invasive species, and in 1950 they introduced rabbit myxomatosis virus, which is highly lethal for naive rabbits. The virus is endemic in South America, but to naive populations it is highly lethal, and it was introduced as the means of pest control to Australia. And in 2 years, the population of rabbits decreased from 600 million to 100 million. The remaining rabbits developed partial resistance, and the virus became less virulent, so populations came into a balance, but only after 80% of rabbits were dead. Then the virus made it to France in 1952, and in 1 year 90% of rabbits were dead. The next year it made it to the United Kingdom, and 95% of rabbits were dead in 2 years. And consider that rabbits do not fly by aircraft, they do not ride in subway, they do not gather in huge groups, they do not gather on meetings like this one. So the spread of a virus in human population can be even more efficient, and this can happen any moment. The pandemic of COVID showed that our health systems are completely inappropriate to contain spread of the virus. And it's not so much a scientific problem, but more a social problem, as it turned out. Another example, epizootist of Ebola virus in Equatorial Africa killed 50% of ape population. And again, in humans, these viruses can spread even more efficiently. So from all that research of virus emergence, there is also a practical application, practical yield. The same methods can help us to trace outbreaks in human population and to introduce proper epidemiological measures. I will just give a few brief examples. Almost 10 years ago, we had an outbreak of meningitis in one of the cities in southern Russia. Here are red viruses from outbreak. And at that time, these viruses were unknown, so there were Chinese viruses and Russian viruses. And of course, as the virus was most similar to Chinese viruses, the immediate decision was to close the border with China. But then the investigation, which unfortunately took a few months, found that viruses that were isolated in Russia over the previous few years, they circulated in Russia and neighboring countries. The virus was there all the time. It did not cause outbreaks for some reason. Nobody knows why, but it was definitely not introduced from China. So the decision to close the border was completely wrong. And this is an example how a timely investigation can promote proper measures or prevent measures from being taken. Another example of our work is investigation of leakage of a lab strain of enterovirus in China. They had an epidemic of enterovirus 71 in 2008. And as a control in PCR tests, they used an archive strain of enterovirus, which leaked, as we prove it mathematically by the sequences, leaked into the environment, and it started circulating in the population. It had been circulating, it was gaining additional mutations to increase its fitness. Then the virus disappeared by itself, and luckily it did not cause health problems. But this is an example that these happen, and they can develop. Also, this dimension of virus sequences allows us to know much more about viruses. Here are evolutionary relations of a virus that causes many, and all the viruses on this tree, very good clinical lab, they are all completely the same. Clinical not see anything at this resolution. They only know it was enterovirus number 11 and no more detail. But when we look at the genomes, we see the sources of introduction, and we, for example, see that Russia gets its viruses from Europe, from China, and from India. We see that, again, it's even for a very good clinical lab, but we see that some groups cause meningitis commonly. So this group was isolated equally from sewage and from meningitis patients, and this group was isolated only from sewage. For surveillance, it's all the same virus. And this diversity was generated, numbers are years. So the different properties of this virus were generated just a few years ago. Here we see that one group is highly transmissible between Russia and India. It goes there and back on a regular basis. And another group circulates only in Russia, and these groups emerged only 15 years ago. So viruses create new features. In most cases, we do not know any features because our technological capacity, even in most developed countries, is not sufficient. The main problem now is not just getting sequences, but comprehending and analyzing them. But still, we lack technical capacity to get enough data. With viruses, we have a lot to learn. Now, a few more slides about our other dimension of work. As you know, Aedes albopictus mosquito, a vector of viral tropical fevers, is spreading everywhere in the world, and in the last 12 years also in South Russia, in the Caucasian region, spread over all the coast and inland. What is important, so we are tracing its spread, and what is important, this spread occurs in perfect accordance with climate forecasts that have been done over 10 years ago. So far, this map, which was just inferred just by climate data, almost perfectly reflects actual spread of the mosquito. It means that climate predictions work, and it means that they are important in projecting what will happen in 10, 20, 30 years. And also we were surprised that although this population was introduced to Russia from a common source, over 10 years mosquitoes have been able to create a huge diversity. So to put it simply, we see adaptation in each nido, in each valley, adaptation in different ways, but these invasive mosquitoes are that they have been known for their adaptability, but its degree is surprising. So we sequenced about 200 full genomes, and we see that in 10 years the complexity that they generated in this small region is awesome. So on this I would like to end, and I would like to thank organizers for the invitation. Thank you very much.
Thank you. Merci, Monsieur le professeur Dr Lukachev, pour cette présentation sur l'éradication des agents pathogènes, ainsi que l'importance du diagnostic pour détecter les cas des épidémies. Alors maintenant, on passe tout de suite la parole à la deuxième Deuxième présentation qui représente donc Monsieur le professeur Simbasson Arsène.
Merci beaucoup d'avoir donné la parole. Mais avant d'entamer notre présentation, permettez-nous de présenter les mots d'excuse du professeur Simbasson Arsène à cause de son absence. Il a vraiment participé à ce symposium, mais à cause d'une mission qu'il ne pouvait pas décliner, il n'a pas pu venir. Quant à nous, c'est un honneur de participer à ce symposium. Mesdames et messieurs les ministres, chers maîtres, chers collègues, l'environnement avec toutes les espèces qui vivent, et tandis que l'environnement, c'est tout ce qui nous entoure, c'est tout ce qui n'est pas moi, selon Einstein. Et en santé environnementale, ce sont les